Hello everyone, welcome to another problem session. So today we have a class of problems where you place a charge next to a metal sphere, a metal plate, maybe two metal plates touching each other at an angle. Maybe you have a metal sphere with a cavity, place a charge inside there. Doesn't have to be at the center, can be off center here. So how do we answer these kind of questions? Okay, so let's see. You already know if there's no metal sphere. So let's recall that so this is the entire system, you have only one charge and no metal around. Then we the electric field lines come out of here in all direction, right? And this is a positive charge, and if I go a distance over there, then you can actually write the electric field will be in this direction. So electric field will be in that direction, and we use a unit vector in that direction. And if the distance is r and the charge is q, then electric field at that point P is kq over r square, and that's the unit vector. If the charge is negative, the electric field will be in the opposite. If this was positive, electric field that way. If this is negative, electric field will be in that direction. You know this, right? So we also write down the potential. What's the potential will be there? Well, it's not a vector, and it's just kq over r, distance from here to there. And this is with a reference that when r equals infinity, very far from the charge, reference 0 v when r equals to infinity. So that's this formula requires the reference. Okay, so now we have something like this. What happens? So we're going to look at a couple of different ways. Let's first look at this couple of different steps. So you have a metal sitting there. This is uncharged. Say we're going to use metal for perfect conductor. What does a perfect conductor mean? We're going to learn later on electric current. We're going to have electric current density J is proportional to something that's called conductivity times electric field. So this is at some point P. So this is some point P, so it has some r and some time t, and this is some r some time t is at that point. So this is a relationship we're going to learn later. This is a current density. You can convert this into the current. So suppose this is the wire, and we're looking at a point in the wire. Then at that point, the current will depend on this area of cross section A. Current will be just multiplying by A here, sigma A, and the electric field at point P. So if the current is electric field or current, if there's a current going around, then there will be electric field. You can see there's a current going around, and sigma is some finite number, right? For the ideal case, we say sigma is infinite. So sigma is infinite. If sigma is infinite, then you can say at this point P, electric field will be 0. But for any finite sigma, which is the regular metal, if there is a current, then there will be electric field, and that's why we want to work with a static condition. So this is coming up in the future. So consider now this uncharged. There's nowhere any charge, and I bring a charge here. So at t equal to 0, this is the situation, and this is plus charge. What we'll do is negative charges in this thing, negative charges in this thing, there are electrons, and positive charges are fixed. But negative charges are mobile, and they will start to move towards this end. So there, then I is not 0 at any point P inside the metal, and EP is not 0. So this is T. When I bring it, this is situation T up to some point, and then this situation will turn into, you have a positive charge. You will have this end will become negative, and this end will become positive. And you can see that inside here, no current becomes 0, and current becomes 0. Then no matter what sigma is, electric field will be if sigma is finite, then electric field, you can see if this is 0, the electric field has to be 0. Electric field equal to 0. So electric field inside metal, and this is the static situation, will be 0. And this would be this will be the case. If electric field is 0, then you can see now that if I go from some P1 to some P2, okay, so from this P1 to P2, if you do the electric field integral, so if you do E dot dl, take a minus, so this will be VP2 minus VP1, this is 0, then this integral from P1 to P2 will be 0. That will means that potential will be everywhere same. So in a metal, we find that the potential is constant, and this is something we're going to use. Okay, so let me pause and clean. Okay, so let's start to solve this problem. So if I have a positive charge, then this is not static yet. So in a static situation, you'll have negative charges here. So you might say it's kind of, this half will have negative charges, and this half will have positive charges. Whole thing will distribute it so that inside the metal, it will be done so that the E at any point inside equal to 0. This is the net. So this charge, see particular point here, this charge is creating potential here, field here, this charge is creating field here, this charge is creating field here, all those fields added up to 0. So point P, E at point P will be E by plus Q at P plus E by all these negative charges at P, all positive charges, E by all the positive charges at P. All of this ends up to be 0. So everywhere along I'm inside. So let's see what the electric field will look like. Electric field will be, let's see, you can see that will be one field line, Of course, around here, if you're very close to the charge, electric field lines are all going like that, right? Over here, electric field line will be perpendicular to the surface because it's a constant surface, constant potential. If you have a constant potential, then the electric field lines will be either in here if this is negative. If somewhere is positive, electric field lines will be 90 degrees, 90 degrees to the surface. If the metal was like that, and this is positive, electric field line will come out over here, but over here is going to come out that way. Always 90 degrees to constant potential surface. Okay. All right. So now we know the electric field lines will have to come out this way, which means some of this line has to bend like that. Some of these lines has to bend and bend so that when it hits it is 90 degrees. It has to bend to 90 degrees. This has to bend to the 90 degrees. And some of these will go like that, and this goes straight line, this go like that. And on this side, electric field lines will come out that way, come out that way, come out that way. It's going to be 90 degrees, 90 degrees, 90 degrees. So these are electric field lines over there. The questions about electric field lines. So that we're done with one. How about two? So here, maybe we should draw a cross section because it's infinite. So let's draw it out like a cross section. So this plate is a cross section, and this is plus Q. So with that view, we'll have interesting thing. This side will pull all the charges. There will be more charges near here and less charges out there. And where it come from? It come from inside here. So this side will become, say, positive, positive. This whole thing is neutral. So, and okay, so now we do the same kind of thing as over there. So we, in here, very close to this, if I'm very close to a charge, it's going to be just like a single charge, doesn't know about that. But over here again, it's going to be 90 degrees. So this is going to hit at 90 degrees. So this will be one line. Over here, 90 degrees that way. So this or some other field from here, I'm going to bend and hit it 90 degrees. And some other will go out there and bend and hit 90 degrees. So it's going to be symmetric like that. 90 degrees, 90 degrees here. It's going to, somewhere is going to go hit, and one will go to infinity like that. And this side we don't write anything. Electric field in the body will be 0, and we can say this one, this, if this goes forever, it doesn't even no bending. All of these are just vertical. It's going to be all vertical because coming out vertical, there's no bending tab. So this is a interesting case. So we're done with that. The electric field lines for this are interesting because we have 60 degrees. It's going to be something like that, right? So it turns out if these guys of course, if this is a plate and this is plate, so we are going to have, let's write down another pen, negative around here, negative around here, and so on the other side will become positive around here, positive around here, and it's going to be almost like that. 90 degrees, 90 degrees, and so over here is 90 degrees also, so it's going to be 90 degrees on that and 90 degrees on that, 90 degrees on that, 90 degrees, 90 degrees, 90 degrees, 90 degrees, and you can see somewhere here start to have a, both of these start to have effect, and there will be some over here is somewhere here is going to go this way, and some other direction is going to go that way. So this is quite complicated. How about the cavity? Let's do the cavity. Cavity. Let me erase that and let's look at a cavity. So let's look at this case now. Like enlarge this to, and I'm going to make it a little bit off, and here is the center of this larger sphere. So if this is a positive charge, then it's going to there are two surfaces here, right? So this will become negative, and outside will become positive. And because this electric field is zero, the outside positive will be distributed pretty evenly. This will be evenly distributed. Over here is going to be more negative here than out there. Let me write on the negative a little bit. Negative will be more negative here than over there. Okay, there's higher density here. So if I look at the electric field lines, it's going to be 90 degrees over here, 90 degrees on this inside, 90 degrees on this inside, 90 degrees on the tangent, 90 degrees, tangent 90 degrees. So this will be the electric field inside, but because electric field lines don't continue on, this electric field zero, these electric field lines will all want to come out this way. As if the entire charge was so. Let's look at if you look over here, if you draw a Gaussian surface, say this is Gaussian surface, and say the electric field is zero on the surface, right? So if you do E dot dA on this surface, you're going to get zero. This is the left hand side of the Gaussian law, and the right hand side says how much charge is enclosed. There's a charge on this inside part of the cavity and this original charge. So you had a right side plus Q inside surface. Total surface charge inside is going to be that. So now equate that. When total charge inside surface of metal is actually minus q, which means that much electron were taken out of here. So the extra positive will be total charge of this whole thing outside surface. Q at outside surface is going to be plus q. So if you put a cavity in here, then actually you can say that this whole thing is simply a problem of a spherical surface with a total charge plus q. So if I was over here, if I had a point over here, point P, and from the center this was the distance r, then the electric field over here will be in that direction, and this will be as if you have a plus q charge sitting there, not over there but over there, and E at P will simply be kq over r square and this U hat. So that's the electric field, and the potential over here will simply be kq over r with V equal to 0 at r equals to infinity. So this is the case. Now I was going to do this, but already I'm 22 minutes in the video, so I will try to do this at another time. One way this thing is done is called methods of images and method of images, and you may want to study this. I think I have some examples in this website, www.physicsbootcamp.org. I hope this was clarifying and helpful to you. If it was helpful, please put a like button to that, and I'll appreciate any feedback that you give me. Thank you very much. Take care. Bye.